All right, welcome back, everyone. So today we're going to go ahead and look at a brand new component. This component is known as the diode. That's what it's called. Okay, and let's go ahead and let's draw a couple of diodes. So first off, we're going to have the schematic symbol, which looks like this. And on one side we have what's known as the anode, and on the other side we have what's known as the cathode. Okay. Now the whole thing about a diode is that a diode only allows current to flow in one direction. You can think of this as a check valve. It's only going to allow the current to flow in the direction of the schematic symbol looks like an arrow. So the arrow is pointing to the right. It's going to only allow current to flow in this direction. Okay, and we have some terminology for this. So I'm going to put up two examples side by side. Let's go ahead and we're going to take a DC voltage source. We're going to hook up a diode like this. And we're going to take another DC voltage source and we're going to flip the direction of the diode. And let's talk about these two situations. Let's say that this is 5 volts. Let's say this is 5 volts. And positives up here, minus down here, positives up here, minus down there. And now I will reiterate, current always flows from a high voltage to a low voltage. Current always flows from a high voltage to a low voltage. So the situation that we've set up in both of these schematics is that the current is going to want to go in a clockwise fashion through both of these circuits. However, look at the orientation of the diode in this case. Remember what we said. Diode will only allow current to flow in this direction, to the right, in the same direction and orientation of the diode from the schematic symbol perspective of an arrow. So in this case, it will allow current to flow. This will allow current to flow downward through this diode. I is greater than 0 amps, okay? Now, in this case, notice that the current is going in the opposite direction of what the diode will permit. Therefore, this is going to not allow current to flow. I will be equal to 0. So in this case, I will flow. In this case, I won't flow. Okay, and we got some special terminology for this. If the diode is permitting the current to flow through it, we will refer to this as forward biased. Forward biased. Okay, biasing is a fancy word for saying applying a voltage to, applying the polarity of the voltage a specific way. Fancy term for Okay, so don't get caught up on the biased part. And forward, because we're putting the current forward relative to the diode. Okay, so forward biased, this is the key word, please. When you see a diode configured such that the current is permitted to flow through it, we will always call that forward biased. Okay, now if the diode is orientated such that it will not permit the current to flow through it, and in this case, this is reverse biased. Okay, now, so forward biased is allowing the current to flow through it. If it's allowing the current to flow through it, it is behaving like a closed switch. Sorry, I have spam calling me right now. If our diode is reversed biased, it's going to behave like an open switch. It is not allowing the current to flow through it. For all practical purposes, this diode is open. And for all practical purposes, this diode is closed. Okay, so we can think of a diode as a one-way check valve. It's only going to allow the current to flow in the direction depending on how it's oriented and that we apply the polarity correctly such that it's forward biased. Now, this view of looking at whether the diode is conducting conducting or not conducting is referred to as the first approximation. Okay, so with electrical components at this point, when we're learning about this, we start with a basic viewpoint of it. Once we understand that, we get to a more accurate representation of the physical device, and then you get even more accurate as you go along. And this starts to become very apparent when you look at diodes, because a diode, in a very real sense, is a very simple device. It only allows the current to flow in one direction. However, it gets a bit more complicated than that. And so we will be referring to this, whether the diode is conducting or not conducting, depending on whether it's forward biased or reverse biased, will be regarded as the first approximation. Okay, so we would say, to a first approximation, this diode is conducting, therefore it is behaving like a closed switch. To a first approximation, this diode is not conducting, it's behaving like an open switch. The diode's reverse biased. Okay, so here's our basic introduction to a diode. Let's go ahead and let's look at a couple of examples of types of diodes. Now, the physical device generally speaking, a cylinder, generally black, and looks, I mean, it's kind of like about the same size as a resistor. However, we know that a diode has polarity. A diode has an anode, it has a cathode. It must be orientated a certain way for the desired functionality that we want to get out of it, whether it's going to be forward biased or reverse biased. But the point is, our diode does have polarity. One side needs to be connected to the positive, the other side needs to be connected to the minus in order to get current to flow. So as far as a physical device is concerned, they need to give us some way of knowing which way the part is facing. So what they're going to do is they're going to put a stripe on one side. And now, if I want to go ahead and compare to the schematic symbol, notice that that stripe is on the same side as the flat part at the end of this arrow-looking symbol. Okay? This side will be the anode, and this side will be the cathode. For whatever reason, it sticks out in my head that this is the cathode band. I don't know why. If that helps you to remember it, then so be it. This is the cathode band. Anode band just doesn't ring a bell with me. Cathode band makes sense. And let me go ahead and pull out one of these such diodes. Here's a big one. Notice the stripe on the right side. Here's a smaller one. Notice this one's got a little harder of a stripe to see, but that stripe is there. This is a very thick diode. Don't I have some bigger ones over here? No, that's as large as I have in my diode set. Okay. There is also another type of diode. These are known as rectifier diodes. I'll put this down here. We also have something called a signal diode. Now, they are constructed a little differently. Rectifier diodes are made out of silicon. And in the very beginning of 311, we will go into the semiconductor physics of how these guys are constructed on silicon. Signal diodes are essentially the same thing. They only allow current to flow in one direction, but they do have some benefits in one application versus another. These are generally made out of germanium. Germanium is another type of semiconductor material. Now, these are signal diodes. Here's a signal diode. Oh, this is a cool one. Is this a one-end? Oh, very cool. I was looking for one of these the other day. There's another type of germanium signal diode. And so, generally speaking, there are a lot of different types of diodes. However, these are kind of two fundamental ones. And the one that I'm going to use for demonstration, for the sake of getting to the second approximation, is going to be an LED. An LED is a light emitting diode. Now, an LED, as far as the physical device, looks a little different because its intended usage is quite a bit different than other diodes. Okay, so it is a diode, a light emitting diode, absolutely. Only allows current to flow in one direction. The schematic symbol that we use for an LED is like this. It's a normal diode, except we add this little light ray that shoots off from the side. The physical device, generally speaking, they look a bit like this. And here's a couple of different colors. Now, if you notice, again, they need to tell us the polarity of this. Which side's the anode, which side is the cathode. So what they've done here is they've made one leg longer. The longer leg is the anode. The shorter leg is the cathode. And they also try to tell us through a little notch on the side that you probably can't see, but one side has a flat. The flat is on the cathode side. So I guess if I make that side longer and do something like this, there. We have a flat side on the left side of the diode. And so that's how they're telling us the polarity or the orientation, which side is the anode, which side is the cathode. Okay? So these are our physical devices. Now, I'm going to go ahead and use the LED as an example. And the reason I'll use the LED as an example is because when the diode is conducting, when it is allowing the current to flow through it, it tells us so by putting off light. So it's a pretty convenient example case for a diode. And in fact, let me go ahead and do a really simple example here. Remember that longer leg was the anode and the shorter leg was the cathode. And what I'm going to do is hook up a few volts to this. Let's do about 3 volts. And now my red probe over here is the positive side, and this is my minus side of my voltage source. I'm going to take the positive side, hook it up to the anode, and take the minus side, and sure enough, I get light coming off of this guy. Very cool. Okay. It is conducting. This diode is forward biased. Let's go ahead, let's reverse bias it. I'm going to take my diode, I'm going to turn it around, and now the shorter leg, which is the cathode, is connected to the positive, and the longer leg is the anode, and I have that connected to minus. Notice I get no light coming off of this, okay? So in this case, the LED is reverse biased. We're getting no light. Forward biased. Reverse biased. Okay, so kind of cool. Perfect example of a diode being forward biased, being reverse biased, and we get some visual indication as such. Now we get into the nitty-gritty details and start looking at what's going to be referred to as the second approximation. Okay, diodes have a characteristic. Every diode has a characteristic, this characteristic, referred to as the forward voltage. We'll be calling it V sub F for forward voltage. This is specified in the manufacturer's data sheet. Every diode, every type of diode is going to have a slightly different forward voltage. The only way you're going to find that value is either by testing the device or by looking in the manufacturer's supplied data sheet. So let's go ahead and let's take an example where our forward voltage is 2 volts. So I'm going to say V sub F is equal to 2 volts. What does this mean? If my supply voltage, if my applied voltage to the diode is less than V sub F, even though this is forward biased, it is not going to allow current to flow through it. So just like a reverse biased diode, if our applied voltage is less than the forward voltage of the diode, then it will not conduct. Okay, so for example, this diode over here has a forward voltage of a nominal about 1.8 volts. I need to exceed 1.8 volts for this diode to conduct. Let's go ahead and okay, my voltage source only goes down to 1.28, so this actually might still give off some light, hopefully not. Okay, so with 1 0.28 volts applied to it. Even though this is forward biased, we're still applying the polarity in the correct direction. We just haven't exceeded the forward voltage. And in fact, let me go ahead and one up this example by using my voltage, my multimeter to show what the voltage is. Okay, I have 1.27 volts. This diode has a forward voltage of about 1.8 volts. Until I exceed 1.8 volts, this will remain not conducting. So as I crank the voltage up, 1.3, 1.4, 1.5, 1.6, hey, look at that. Once we hit about 1.7, 1.8, notice the LED is now lighting up. It is conducting. Okay, so it's not just good enough to forward bias it, we must also exceed the forward voltage. Okay, so let me go ahead and finish up my drawing. If we then apply a supply voltage that is equal to or larger than the forward voltage, it will conduct. So let's say 2 volts. Okay, everyone good with this? I'm going to pause here for a second. To answer David's question, absolutely, yes. Once you exceed the forward voltage, that gets into the next part of this story. So I will talk about that in about 10, 20 seconds. I just want to pause here and make sure if anybody has questions about that forward voltage. What paragraph? You're talking about this paragraph? Yeah, greater than, equal to, sure, if it makes you feel better. Here's the deal. Forward voltage is a little bit of a floating around value. Sometimes it's 0.7, or let's just say for this diode, sometimes it would be like 1.7, 1.75, 1.85. It's not a hard line. It's not like you just equaled this value, all of a sudden conduct. It's on a continuous range. So you have varying degrees of conduction. It's almost like the switch, that first approximation switch is partially closed, well, where it's allowing some to go through it. Okay, I'll show you the LED blowing up in a minute. Okay, so if we're comfortable with this forward voltage, let's continue on with our story. Once you exceed the forward voltage, the resistance of this diode starts to head off to 0 ohms. Okay? In other words, it starts to look like a short circuit. If our V sub F is 2 volts and our applied voltage is 1.5 volts, we know that this is going to not conduct, even though we are forward biased. This will not conduct. How much resistance is an open switch? Yeah, really good open switch should be infinite ohms. How much resistance is a closed switch? 0 ohms. At least a really good closed switch should be 0 ohms through it. Okay, so once we exceed the forward voltage, we expect that the resistance of this diode begins to drop and heads towards 0. And it actually happens to do that very quickly when you exceed the forward voltage. So in this case, 2.5 volts, 3 volts, we can expect that the resistance really is headed towards 0. Now, what happens to the current through this circuit, the current through this diode, when the diode is behaving like a 0 ohm resistor? Well, just replace the diode with a 0 ohm resistor. We know that once we exceed the forward voltage of our diode, in this case is once we exceed 2 volts, we know that the resistance heads off to 0. Well, if the resistance heads off to 0, it's the same thing as me saying I have an R over here equal to 0 ohms. And just like any other circuit, if we had 0 ohms connected between one side of our voltage source and the other side, then we've just created a short circuit. In other words, we have an unwanted low resistance path between our positive voltage and our negative. And so you calculate I the same as you would any other circuit using Ohm's law, and you get 5 volts divided by 0. Now, obviously, this is undefined, and your calculator would not like you to punch it in, nor would any other mathematician, but this does head off to infinite amps, right? 0.00001 ohms. Obviously, these wires have some real amount of resistance. This diode also has some real amount of very small resistance, but nevertheless, the current goes to infinite. Do you think my LED wants to have infinite current flowing through it? No, the diode's going to go up in flames. Doesn't like this situation. Let's go ahead and see it. Now for this case, I'm going to go ahead and hold up the diode so I don't burn my notes. These are pretty cool. These are little helping hands. I use them for soldering and I use them for other things. They do a pretty decent job at holding things up in the air. So same exact example. I am forward biased. And I will show you what the voltage is. I'm going to use my smaller multimeter so I can fit it onto the screen. Black probe always connects to the common. Red probe always goes to the whatever quantity you are measuring. In this case, I am measuring volts. And now, hopefully, you have a good view of my diode that I'm about to send up into flames. Okay, right now I am at 1.2 volts applied to this forward biased diode. As soon as I hit the forward voltage, I should begin to conduct. I should get some light coming off of it. That'll happen at about 1.8 volts. No light, no light, no light. I start getting some light coming off of it. Okay, now let's go ahead and let's exceed the forward voltage. Now we're hitting 2 volts. Notice how bright that is. That is getting super bright. Okay, we're now putting about 5 volts into it. And I can see that, wow, it's starting to turn orange at 6 volts. Notice it's starting to die. Okay, the light's actually dimming even though I'm applying the same voltage to it. And I'll crank that up a little further. Maybe we'll get a little smoke coming off of it. 8 volts, 9 volts. This is loving it. Okay, and I just killed this diode. It's even looking a little blackish on my screen, and the diode's now... Oh, that smells terrible. Okay, burnt silicon. What happens if I touch it? Well, I'll probably burn myself. What's the average lifespan of a diode LED? It can be a very, very long time. Okay. Oh, yeah, that smells awful. Oh, okay, good. I did not burn my expensive connectors over here. So this diode, word of advice, when you burn out a component like this, throw it away. Don't put it back into your parts bin. If you put it back into your parts bin, it just guarantees that you're going to use a bad diode at some point in the future. So into the trash with this guy. Cool. Okay, so how do we fix this situation? I would like to power an LED off of 5 volts. 5 volts is pretty common. Many digital devices work with 5 volts. Generally speaking, I have access to 5 volts or 3.3 volts. All of those are much larger than the forward voltage of my LED. And yet I would like to use my LED for indication, to let me know that the power is on, to let me know that something is on. So how can I fix this? I need something to limit the current through this series circuit. Help me out. What do I do? A resistor. Perfect. What do I do with that resistor? Slap a resistor in. Do I put it in series? Do I put it in parallel? Somebody said add a resistor, so let me go ahead and add a resistor. There, I added a resistor. Is that going to... Okay, series, right? add a series resistor into this circuit. All right, what's my value of resistance? All I know right now is I have a diode that's got a forward voltage of 2 volts. And this is going to be an LED for this example, so let's make it an LED schematic symbol. Okay, now here's where the art comes in. 4.7K, 10K. So it depends on how much current we want flowing through this. In fact, I will go ahead and call this desired I equals something. Okay? So we need to either pick a resistor and then calculate the current going through it, or we need to set what desired current we want and then pick a resistor to match that. So let's go ahead and come up with a rule of thumb for general purpose indication LEDs, just like the one I fried on my desk. $10 milliamps. Okay, the max current that these general purpose LEDs can withstand without breaking is 20 milliamps. But just because something can take 20 milliamps doesn't mean I should give it 20 milliamps. Okay, generally speaking, not a good idea to run components at their max rating. General rule of thumb of that is derate it by about 50%. So if my max is 20 milliamps, then the most that I would want to run through this would be about 10 milliamps. Now at 10 milliamps, I promise you this LED is going to function as its intended purpose of the case of indication very well. At 10 milliamps, this will be sufficiently bright enough to let the user know during daytime or in their room when the lights are on that something is on or that something has happened. So for its purposes, 10 milliamps is a good rule of thumb for these types of general purpose LEDs. So now we have a desired current through this. All right. Now we know that we have 10 milliamps flowing through this circuit, or at least we will once we put this resistor into place. Now, for a series circuit, my current is the same at every point. So if I have 10 milliamps going through here, I got 10 milliamps going through here. Well, if I know that my diode is conducting because it's forward biased and the supply voltage is exceeding the forward voltage, then I should be able to calculate a value for this resistance that gives me 10 milliamps flowing through this series circuit. Now, here's the next piece of really important information that I haven't told you yet. When the supply voltage exceeds the forward voltage, the voltage drop across the diode is equal to the forward voltage. In other words, V sub D is equal to V sub F when conducting. So now we know that the voltage drop across this diode is equal to 2 volts. So if I have 2 volts across my diode, what's my voltage drop across this resistor? Right? It's just Kirchhoff's voltage law. If I have 2 volts across my diode, then the remaining voltage, 5 volts minus 2 volts, gives me my voltage drop across the resistor. Therefore, in this case, I have 3 volts dropped across my resistor. So now that I know that I want 10 milliamps flowing through my resistor and that it has a voltage drop across the resistor equal to 3 volts, I should be able to use Ohm's law to determine what R is equal to. Well, what is that? V equals IR. Therefore, R equals V divided by I. So I have 3 volts divided by 10 milliamps gives me my value of resistor such that I will get 10 milliamps flowing through this circuit. Let's calculate what that is. Why is my calculator so large? Better. Okay, so 3 volts divided by 10 milliamps, 300 ohms. Okay, I'm going to go back to chat now. So Jackie, no, not 4.7K or 10K. 300 ohms if I want 10 milliamps going through this circuit. Okay. Let's go ahead and set up this example a little more realistically. I can't buy a 300 ohm resistor. My forward voltage of this diode is not 2 volts. It's more like 1.8 volts. And to pick my resistors such that I get a desired current when I don't have 300 ohms, no, but a very close value is 330 ohms. Aiden just wants to slap in resistors. Okay, so let's go ahead and set up this example more realistically. Generally speaking, I have constant voltages in my circuits, and 5 volts is a pretty common one. My resistor, a value close to 300, is 330 ohms. My general purpose LEDs generally have a V sub F equal to 1.8 volts, and we did see that when we were slowly cranking up the voltage in an earlier demo. And let's go ahead and calculate what the current is going to be through this. Now, if my diode's conducting and the applied voltage is larger than the forward voltage, then the voltage drop across him will be equal to V sub F. Therefore, V sub D is equal to 1.8 volts. That means that 5 volts minus 1.8 volts is my voltage drop across the resistor. Take that voltage drop, divide it by 330, and we will calculate what I is equal to. So I therefore is going to be equal to 5 volts minus 1.8 volts divided by 330 ohms, which should give us a current of 5 minus 1.8 divided by 330, about 9.6 milliamps. Okay. Here's our values. Let's go ahead. Let's grab a 330 ohm resistor. There's my 330 ohm resistor. Here's my hopefully not burnt out LED. I'm going to set this up using a breadboard. And I got just the one. Pick a color. I got yellow, white, black, green, blue, green. Look at that. I got a green breadboard. Let's go ahead and take the anode of the diode. And I'll put that in there like that. And then I'll take my 330 ohm resistor. And I'll put that in my breadboard like that. And I'll bend this so you can see it a little better. And now what I'm going to do is take my voltage source, and I'm going to connect the minus side down here and the positive side over here. However, I would like to see the current flowing through this. So I'm going to take my multimeter, I'm going to measure in the milliamp range. So I'll put my black probe into the common and my red one into the milliamp range, and I'll set my multimeter for milliamps. I'm confident that I'm not going to exceed 200 milliamps because, well, I designed this circuit and I know what I'm doing. So as long as I don't exceed my, actually in this multimeter, it is a 500 milliamp max fuse rating. As long as I don't exceed 500 milliamps. On other multimeters, if you're using the milliamp range, you'll see that it may have a max of 200 or 250 milliamps. As long as you stay under there, you're safe. If you exceed 200 milliamps, then you blow the fuse inside. You have to replace the fuse. Okay, so the bottom red multimeter will be for current. I'm going to now have to cut my circuit for measuring current. And I'm going to connect it to one probe. And then the black probe, I'll go ahead from the top here. And now the current is flowing through my multimeter into the resistor, through the diode, and back to ground through the black wire. I'll also be taking some voltage measurements. So I'll use the orange multimeter over here for measuring some voltages. Okay. Right now, well, let's see. I want to take some notes as I do this. Okay, is that readable on your screens? Nope. Yes. Yes, yes. Okay. Unfortunately, I'm a little out of space, so... Wait, yes. Okay. So right now, I have... Can I fit the circuit in here with my values that I calculated? What should this be? 9.6 milliamps. Okay, so right now I have 1.26 volts applied to my circuit. 1.27 according to the multimeter. So, is the diode conducting right now? No, right? We have no current flowing through it. Our multimeter measuring current tells us such. Why don't we have current flowing through this? Because the applied voltage has not exceeded the forward voltage. The forward voltage of this diode is 1.8 volts. We're at 1.27 volts. We haven't exceeded the forward voltage, therefore it's not conducting. Therefore, we have 0 amps flowing through this. Let's take this up to let's take it to 2.5 volts. Okay, so we're at 1.27. Let's take this up to 2.5. Okay, notice now our LED is on. We have 2.5 volts, so we've now exceeded the forward voltage. Our diode is conducting. What should the forward volt... I just answered my own question. What should the voltage drop across the diode be right now? Voltage drop across the diode. 1.8 volts. V sub D should be equal to V sub F because we are conducting. So let's go ahead, let's measure the voltage drop across the diode. Check that out. 1.85. We're 0.05 volts off from the nominal forward voltage. This is totally normal, totally fine, and to be expected. The forward voltage is not a hard set value. It does fluctuate a little bit depending on usage, temperature, humidity, and the way you look at it. Okay, so 1.85 volts. So if I have 2.5 volts applied and I have 1.85 volts dropped across the LED, how much voltage drop should I have across my resistor? Right? Kirchhoff's voltage law says I should have about 0.65, 0.7 volts across my resistor. Let's check the voltage drop across the resistor. Hey, check that out. 0.7, 0.65, almost exactly. Okay. Given the length of all these cables, given the breadboarding, all of that, I expect to be off by a little bit. This one happened to be spot on. Okay, so I have 0.65 volts across my resistor. So somebody punch into their calculator the Ohm's law calculation of 0.65 volts divided by 330 ohms. .65 divided by 330 ohms. This is just Ohm's law. Gives us a current of 1.969, 1.97 milliamps. That's exactly what I'm getting through this, right? Okay. So at this point, everything's agreeing with our calculations. Let's bump this up to our intended voltage of 5 volts and see if we get 9.6 milliamps through it. I'll probe the voltage applied so you can see that as I raise it. Here's a really cool probing technique when you're using breadboards. The plastic here is not conductive. There's no way that you can probe a wire going into another one of these holes in the same group of 5. But what I can do is I can probe the conductor where it enters the breadboard, and it gives me a nice convenient place to slightly push down so that my probe is held in place while my hands do other things. I'll do the same thing for this one over here, where the probe goes into the where the LED goes into the breadboard. I'll just slightly push down there with a little bit of pressure, and now I'll hold them both with one hand. Now you can see the voltage. I'm going to go up from 2.5. We're going to raise this up slowly till we hit 5 volts, or as close to 5 as I can get it. Okay, I'll take it. 5.01 volts applied to the circuit. What did I get? 9.04 milliamps. All right, why is this off from my calculation? It's a bunch of reasons. First off, my resistor might not be exactly 330 ohms, except I get the feeling it is pretty close to that. I get the feeling that my forward voltage has changed a little bit because I'm passing a bit more current through it. So let me go ahead and probe this. Now, if my current is lower than 9.6 and my resistor has not changed, then I get the feeling we have less of a voltage drop across the resistor. We would have less of a voltage drop across the resistor if we had a slightly higher forward voltage. So let's go ahead and let's just measure that. Okay, check that out. Instead of 1.8 volts, notice my forward voltage with about 9 milliamps flowing through it is a little higher than what I initially said, 1.8. It's now 2.03 volts. That's totally fine. Like I said, the forward voltage is not a hard set value. For this reason, when we take the forward voltage to be a constant value, we refer to this as the second approximation. In our case, we took it to be a hard set value of 1.8 volts. Okay, let me give you some general rules of thumb for different diodes. Rectifier diodes, generally speaking, are constructed out of silicon and have a nominal forward voltage of about 0.7 volts. Signal diodes are constructed out of germanium and generally have a nominal forward voltage of about 0.3 volts. LEDs, or light emitting diodes, are a completely different beast and animal. They're constructed quite a bit differently so that they produce that side effect of light, and they have a nominal forward voltage of about 1.8 volts. And don't ask me how LEDs are made, because I have forgotten how. I used to know. I think a few years ago. And then it's just one of those things that I just haven't thought of in a while, and so I have forgotten the process of making them. It's one of those things, if I just go and read for about 10 seconds, I'll be like, oh yeah, duh. Okay, so hopefully, let's see, we started at 9:30 and we ended 10:47. So hopefully this makes sense. Hopefully we understand diodes. I hope my demonstrations were good, and I hope this was easy to follow. Okay. I'm fine without covering anything more with this. Next up, we will apply some AC to this diode, and we're going to now take what we learned the last two lectures with transformers and AC voltages, and we'll apply them to a diode circuit. We'll see what the result of that circuit is, and then we'll go back to capacitors and inductors in AC, and I get the feeling we'll be finishing up the semester on that note. Okay? All right, so I'm going to stop recording now. If you have any questions, I'll be happy to stick around.